So just point out my collaborators here in Rochester. We're all based in Rochester, except for Joe now, who's based in Alberta, but he was in Rochester, and at these two institutions. Right, and many of us are here at the conference. Okay, so the outline is, can everyone hear me? Is it loud enough, or should I use the mic? So why are we interested? Where do we want to go? What is the basic strategy? What is our progress so far? And how best to set up the problem? First of all, why are we interested? Well, a lot of this we've been over yesterday and today, but basically the transients, a lot of people are interested in transients, and we're going to hear about those in more detail. Certain types of stellar explosion, including the supernovae of type 1a, which we'll be hearing more about again. Planetary nebulae, pre-planetary nebulae, especially the bipolar kind. Observe post-common envelope binary systems, the statistics and the origins of those systems we heard about yesterday. And then, of course, the gravitational wave emitting mergers and all the statistics about those. So where do we want to go to address these, to answer these questions? Well, we want to look at modeling the transients by getting synthetic light curves and intensity maps from the simulations. This is non-trivial, and some papers have been written about this, and Ursula did talk about it as well in her talk yesterday. We want to model the aftermaths of common envelope evolution. For example, shaping of planetary nebulae, which Adam will be talking about. The offsets between the binary central stars of planetary nebulae and the nebulae themselves, which we've looked at in some of our papers, and perhaps Thorne-Zitko objects, which I know some observers are now searching for. We want to predict the post-common envelope orbital parameters, for example, the final separation, the final eccentricity. Those are for systems that eject the envelope, or also this, of course, alpha. Or for systems that don't eject the envelope and actually merge, we want to know about the envelope that remains. What is its mass, and what are its other properties? So ideally, we would want to map out the dependence of these parameters on these independent parameters, the primary mass, secondary mass, the evolutionary states of the two stars, initial eccentricity, and metallicity, and then interpolate between the models to fit scaling relations to the results, and this can be very useful for populations studies. And then, of course, we could also invert the problem to try to infer pre-CEE pre-common envelope parameters from observations. Now, I was thinking about it, and could we do better than alpha? Well, one possibility is to look at the time-dependent quantities, because eventually we might want to go to 1D. I mean, I'm not an expert in population synthesis models, but it might be natural to go to 1D modeling eventually, and then of course to model transients you need that time evolution. So this is one possibility, is to make things time dependent. So instead of basically the usual alpha would be like a mean value of this quantity, we're basically just taking those two, the left hand and the right hand side of the equation, but you're making them the rates instead, and then you divide them, you get like a time dependent alpha. Or you could even separate it a bit differently, since we often use the total gas energy with all the terms, the potential and the kinetic and the internal, as our definition of whether the gas is unbound or not. Of course, that can also be questioned, but then you might want to separate these two sides of the equation differently, perhaps, and use something like this, which I put here as beta CE. So there are possibilities for looking at the time dependence. What about triple and higher multiplicity systems? Could be very interesting. There's some work that's been done on this recently in the Windtunnel model. We need to understand, overall, we need to understand the physics and interpret the simulations, but build simple models to capture the essential physics. So we shouldn't lose sight of that. So what is the basic strategy? And I'm going to just give an overview of what everyone sort of, the approach people sort of take for these simulations. So the first thing is you have to model the primary, which is actually really challenging. It's probably the most challenging part of the problem. And what people do is they first run 1D stellar evolution code, usually MESA. We cut out the core, which we can't resolve in our 3D code, and we replace it with a gravitation-only particle at the center with a chosen prescription for the softening. But then we have to model that whatever's what we took out, we have to model that expunged gas part of the envelope, that core. Well, it's the core, but it's the gas in our simulation, the gas component. We have to model it, and the way this is now done by most of the groups is to solve this modifying Lane-Emden equation as discussed in this paper by Sebastian Ullmann and this group. Then there's the question of what equation of state do we want to use. We use an ideal gas equation of state, but then we won't be able to reproduce all of the properties of the Mesa solution because, for example, if we choose to fit the density and the pressure, then we can match those, but then we won't be able to match the entropy gradient, and then the convective instability that should be there may not be seen. And there are issues like this. So some groups have moved to using the Mesa equation of state. Other groups are sticking for now with an ideal gas equation of state, adiabatic usually. We have to add an ambient medium, as was discussed in the last talk, and its pressure. What people do is they make its pressure comparable to the pressure at the primary surface to help stabilize the primary. So basically, what this does is it intercepts the surface of the primary at a certain pressure, such that you don't go. So it's like you're cutting off the very surface, so that those pressure gradients are smoothed over. So maybe we can improve on this, but that could be the point for the discussion. And then we have to, now some groups then relax the primary, use it by damping the velocities, just leaving it sort of stationary in the simulation and damping the velocities. They have this algorithm for relaxing the velocities, and other groups don't do it. Is it necessary? In our case, we find that we've tried it, but we find that in some ways it helps a little bit, but it's not really worth it.
Sure. Trying to study stability of mass transfer, you need to know how the surface is responding. So that's sort of confining it from the outside on possible responses that rise to runaway mass transfer.
I mean, we expect that I think the thing we have to do is to look at a convergence study. We have to try different ambient pressures and just see what difference it makes. I don't know if people have done that. I mean, I wouldn't expect it to make a big difference because at the surface, things are very low density. And so probably the surface, the mass loss wouldn't be affected very much by putting in that high pressure. But it's a good question. I mean, it should be tested. So then the next thing we have to do is to model the secondary, and we do it. We model it also as a gravitational point particle. This is maybe okay if the softening radius is greater than the stellar radius, but for main sequence stars, the two things are comparable. And so ideally, you would have some kind of subgrid model. We set the stars in orbit, some initial separation, but then which separation is the question. It's been argued that putting it at the Roche limit separation is more realistic. You get circumbinary forest that can be important to shape the common envelope outflow that happens subsequently. Is it important for the mass loss? Still not clear. We need to specify the rotation of the primary, but what exactly different groups specify, choose different rotations. We let the code do its thing. We have algorithms to determine where to concentrate the resolution, how to change the softening or smoothing length with time, if this is a good idea, not clear. And then the equation of state as well. So this is an example of one of our simulations in the co-rotating frame of the orbit of the particles. So the secondary is here at the center, and it forms a trailing spiral pattern, but in this frame it's a leading spiral pattern because the gas lags the particles in their orbit. And we use, this particular simulation has a mass ratio of 1/2, so the secondary is half the mass of the primary, but it's more massive than the core of the primary. And we started at just above the surface of the primary, and we have 0 initial spin and 0 initial eccentricity. That's just an example, And this is the same simulation, but now in the box frame, so the center mass frame. And you can see that what happens is that, I mean, what I'm showing here is the red corresponds to unbound stuff, where unbound is defined as total gas energy greater than 0, and the blue corresponds to bound stuff. And as the secondary comes in, it basically rips off material, and that stuff flows out, and then it eventually catches up to the tidal bulge, the posterior bulge of the primary, and basically runs into it, forming a shock. And at that point, it sort of stops unbinding things in its direct vicinity, because that material has trouble getting out of that dense region. And so you end up with this dynamical plunge-in phase that precedes that. You end up with a lot of unbound mass, but then after that, it sort of tends to flatten off on all the simulations.
Just to be on the same page, unbound defined as?
So here it's defined as the total gas energy being positive, and total gas energy is all the terms, so like internal, bulk kinetic, potential, gas potential, gas.
Including thermal energy.
Yes, in this case it's.
Right. But you wrote over there, it's the E kinetic potential gas, that's the total kinetic.
That's a total.
Mechanical.
No, because kinetic here include. Oh yeah. So in our paper we say thermal internal is kinetic also. So we have kinetic. We have internal and bulk. Those are that we use in every notation, but it's all in here.
Okay.
Yeah. So that we should have pointed that.
But that's one of the reasons why you are, if you put it just into the surface, is different from putting it across your portfolio. You start with different energies, right? You cannot say anything about unbounding if you started with wrong energies.
Well, no, you could estimate how much extra energy you would have if you started it with at the Roche.
Yeah, but you don't know where it will be
separation.
placed into.
You don't know where it would be.
Where that energy will be applied to. You have no idea about this, right? And you start with the wrong angular momentum. Just
I mean, we're not saying that this is perfectly realistic. I mean, it's because the computation resources that are required if you started at a much larger separation are much greater, and so.
Yeah, this is the difficulty with, obviously, you have to start, I mean, this is, I think, one of the frontiers is we have to ask ourselves what happens if we start at larger radii, which of course involves much larger computational task.
We know part of that answer. Yeah, just so there are comparisons.
Yeah.
Of course, in certain regimes.
Right.
Yeah. It should.
So Ursula's group has started doing that, and Morgan as well.
Right,
so.
but there's only, you can write down your guys' papers, that's it.
Yeah,
Right,
that's
yeah, we go step by step. So this is showing the green is the bulk kinetic energy dominated, and the magenta is the internal energy dominated. And you can see that the stuff that flows out during the plunge-in is basically supersonic. Plot the Mach number, it matches up pretty well. And the stuff at the inside that's being churned as I guess you call this slow spiraling phase, remains, is sort of thermalized. Okay, so you could also look at the parameter space. So this is the simulation I showed. This is the orbital plane, a slice through the orbital plane, a slice parallel to that through the particle. Sorry, perpendicular to that through the particles. And this is different masses of the secondary. So at the same time in the simulation, 40 days. You can plot the separation versus time. You find that the smaller mass companions take longer to plunge in, but then they eventually go to smaller separation. And then you can plot the unbound mass by that same definition. You find that most of it, like I said, is unbound sort of during that plunge-in phase up to the first periastron. And then here we actually have it reducing because of the issue that was mentioned in the last talk about having to displace the ambient medium, which in our case is fairly dense, and having to do work to displace it.
How dense is the ambient medium?
In our simulation, it's the same as the surface of the star, the outermost.
So how much total mass is there?
Quite a bit. I mean, a couple of solar masses, pretty large.
So you want to avoid
We want to avoid doing that in the future.
No, it's not. You want to avoid having really high temperature, right?
That's exact. Yeah, because if you have too high temperature, the sound speed is high, and then your time step gets really small.
Right.
So we experimented with that. found that just try first with large.
But the unbound matter isn't like sweeping up so much mass that you're just calculating.
We did some.
Not at the beginning, not during the plunge. So we can be confident about that part. But later on, we have to, we've estimated, it sort of works out. Would be losing space.
Excuse me? Can you explain why first maximizing the unbound mass, why does the unbound mass go down? Is that because of
Yeah,
the box size, or is it like sweeping up mass or something?
Well, it's we try to explain this feature in our paper. It has to do with the way that mass that was just unbound runs into denser material and has trouble, and then because the energy is being transferred between the different forms, it's kind of complicated. Other simulations see this feature also, not all of them, but we do try to go through the details in our paper with the plots and so on.
So you remove 2 solar masses of the code vacuum and only 0.2 solar masses of the envelope. But if you put in all code vacuum, maybe you will be able to remove all 2.2 solar masses. I mean, 2 solar masses is a lot compared to the mass of the envelope.
Two solar masses is a lot. I mean, it's similar to the mass of the envelope, but it's ambient stuff. I mean, it's not affecting what's happening at the center of the simulation. When the stuff gets out to large radius, then yes, it would be. It will transfer some of its energy to the ambient gas. We've taken that into account.
You just showed yourself that this drops down once it ran into that stuff, right? That's why your
Yes.
ejection stopped. You ran into that stuff.
I mean, we don't think so, because I mean I can go through. I can show you the movie again, but because basically once it gets to the center, that material that it's churning up runs into denser stuff and just can't expand. So I mean it's complicated. We don't understand it completely, so we don't think it's because of the ambient that we stop unbinding material at the center.
Have you looked at the unbound mass inside the orbit?
Yes. It's negligible.
Oh, okay, all right. So it's all, the stuff that's being unbound is always outside.
Almost always, 99%. So this is just showing that other groups get the same sort of behavior. All right, well, I've taken up a lot of time with that intro part. I just wanted to go through what the different groups have done. And I put groups sort of in the order, roughly the order where they started working on these simulations, and the various methods and codes. And should also mention these groups, which are doing related things, but not quite fit into what I was talking about. I mean, it's related, of course.
Actually, we do also common envelope binaries and with gadget too, get similar results.
Okay, yeah. So we'll hear from you today, or? So yeah, just briefly. I mean, we've seen talks yesterday about these various groups, but it's exciting recent developments by Paul's group, where they're starting to look at the most massive stars to try to understand these black hole binary systems, and making nice progress now, and getting a nice separation decrease here. These are really large scales that are being used here, so very challenging, and you need radiation transport because otherwise the thermal timescales are comparable to the other timescales in the problem. So you really need radiation here. It's very challenging to do, but everyone wants to get there. Then we heard from Ursula yesterday, and one of the nice things they're doing now, like we just mentioned, is starting their simulations from a larger separation and exploring what happens during the Roche slope overflow. And they've also done many parameter studies and convergence studies. And then Natasha's group are the only ones actually who could eject the entire envelope, and so
Ursula can do too.
With your
Ursula can now do it with
Right.
combination. So that's the only ones that could provide the real final.
Again, what's the
orbital
definition of unbound material? It's very important here. So one need to compare apples to apples when we discuss.
So
Mechanical energy.
they can start to do the things, they can start to do the things that, you know, I mentioned at the beginning of the talk, you know, calculating alpha over the parameter space, the amount of energy in unbound material, and start to look for empirical scaling relations as well. Okay, and we just heard the talk discussing the moving mesh code of Aribo, but they have the highest maximum resolution simulations, and particularly these things that, you know, they have a sophisticated method of preparing the initial conditions. The only MHD common envelope simulation up to now where they do get dynamo and a saturation of the field, they find that it's not dynamically important, but interesting anyway. And then the Windtunnel simulations, where they you know, model it in a Cartesian box. You can put in different density gradients of the envelope, and you can explore the parameter space, for example, the force, the dynamical friction, drag force, and also including the accretion force, the thrust from the accretion of material. And they also look at accretion. And then we've also looked at accretion in our global models. Like we discussed, like I mentioned briefly yesterday, we find very high accretion rates of order 100 times Eddington for main sequence star, and even greater for a white dwarf. These sort of an upper limit, because it requires that, like in our subgrid model, we remove the pressure and energy, and so you would require some kind of pressure valve in reality, and that could take the form of a jet possibly, or for a neutron star it would be neutrino emission.
So for your subgrid accretion model, can you just say a few words what you mean by that?
Yeah, so we assume it's based on the Bondi-Hoyle formalism. And it's a paper by Krumholtz, 2004, I believe. It's very similar to that model, which they use for star formation. It has some slight differences, which we mentioned in the paper. And then, most recently, Phil and Phil's group, they've using moving mesh code, which we'll be talking about soon, and they unbind a large percentage of the envelope. They include recombination energy as well. All right, so the big question is envelope ejection. In most cases, we don't unbind the envelope. We don't eject the envelope. Simulations don't. And why is that? So it only happens when recombination energy is now, our simulation is at least consistent with expectations from the energy formulas. If you take our particular setup and you ask what final separation would you need to get to eject the envelope according to the energy formulas, the numbers are actually really small. And none of the simulations and three of the simulations started with a similar setup, ours, Sebastian's, and now Phil's. And none of the simulations, although they get close to this alpha equal 1, these alpha equal 1 numbers, they don't quite get there. So, and this here I've listed at the initial separation we use, and then at the Roche limit separation for this system. And so, I would conclude that in at least some, if not all cases, the separation reached at the end of the simulation is just not small enough to eject the envelope. And we also heard from Ursula, who mentioned that it's not small enough to understand observations, where the periods that are observed are on orders of days or less. So what is preventing the simulations from getting down to these small separations? Is it insufficient duration? Well, if you look at Sebastian's thesis, you find they do get another phase of unbinding towards the end, but then Rudiger tells me that they're not confident about, as he mentioned in his talk, about the energy conservation and so on, and so they stop the simulation. So could it be that just continuing the simulations, perhaps we need more fidelity, but to continue them beyond a certain point would help with this. You need more resolution, perhaps. People have done resolution studies. There seems to be convergence in the Rudiger's Sebastian simulations, but it's marginal. It's not clear whether. So this is the amount of resolution elements per softening length. What all the different studies conclude is that as this number gets larger, the mean separation at the end of the simulation gets smaller. So it's not clear that everything is converged with resolution. And the softening radius itself.
So that a RSoft over delta, is that a statement for SPH? What RSoft you mean is gravitational softening? What?
Yeah, so this is more, I mean, so this is more for the mesh codes. And then I also said number of particles. So if you look at the number, so I think it's this one, right? It looks at number of particles and varies the number of particles. And they also,
I see.
it's not quite converged. So either one.
All right. Okay. It's not RSoft divided by delta. RSoft comma delta. Okay.
No, it's divided by. Like delta is the smallest resolution element,
Right.
the size of that, and RSoft is the softening radius. So that number needs to be large. And then the softening radius itself affects the gravity, and hence the density distribution, and hence the orbit as well. So in our case, we did something cruder than what Sebastian's paper did. So we just have the softening radius at some point during the simulation. And this is a measure of the mass around the secondary within spheres of a given radius. And you see that it plateaus here, but then as soon as we reduce the softening radius, the gravity increases, and you get more mass accretion towards the secondary. And then again, it piles up around the secondary, as you would expect. This is the case without accretion.
So this is a
Without an accretion
This
model.
softening rate is at the core
No, this is of the secondary.
of the secondary.
Yeah.
Okay.
So, but it shows that you know, by reducing the softening radius, even if you do it gradually, that can affect the amount of mass and the mass distribution around your point particles.
So what about the energy which you can extract from the binary orbit as a function of chosen softening value? I mean, you observe some distance between your cores, right? So you can calculate what the energy it has in reality,
Yeah.
and then you can compare that to what your softening
Yeah.
description does.
That's a very small correction. We've looked at that, and it's mentioned, the number is mentioned in our paper. I don't remember the number, but it's a relatively small correction, about 1 or 2% of that order. Yep.
So Natasha and I were just talking about the speed with which things destabilize after material starts leaving through L2, and I wonder if this might have something to do with that. How fast you fill up the rush lobe of the secondary, and how fast it starts losing matter from the whole system.
Yeah, that's interesting. I mean, I think we need to do more convergence studies with softening length as well as with resolution.
Yeah, because a deeper potential in that around the secondary would retain more.
Right, so then another possibility is just a non-optimal parameters. We're all going after the red giants, the low mass red giants, which are relatively easier because of the smaller dynamic range of scales, both time and space. But perhaps it's not optimal because if you look at, for example, the AGB with the same mass, which we've also modeled and for MESA, same MESA simulation, we just evolved it longer. And when you use the alpha formalism, you only need to get down to separations of around 10 instead of around 3 at alpha equal 1, or it would be, if alpha is 0.25, it would be, but the separations you would theoretically need to get down to are much greater. So that could be another issue, that we're all focused on one region of the parameter space. Or it could be that there are effects that lead to this unexpected stalling, or at least a prolonging of the in-spiral. And recently we've been working on this, and we've plotted the force, the drag force, as a function of time that we get from our simulation. You can look at the phi component of the force on the secondary. That's the orange line. Or you can look at the component along the velocity, which will be different in general because there will be radial motion as well, especially during the plunging. Positive here is a positive drag force, a negative force in the direction that it's moving. And then if you plot the analytical values according to the Bonnier-Littleton theory, but using, so here as the velocity, I'm trying to make contact with the Windtunnel simulations. I've used the relative velocity between the core and the secondary. And for the analytical numbers, I've chosen the density in the envelope that you would, at that separation in the initial envelope profile. Okay, so at the separation, the current separation in the simulation, what would be the density, what would have been the density in the initial profile, and what would have been the velocity, assuming that the envelope is not rotating. And what you expect is much greater than what you actually get. And in some cases, you actually get a force in the opposite sense. And so it's on the 5% level. This is for that 1/2 mass ratio. For smaller mass ratios, you see that they're a bit closer. But this could be part of the explanation for why your separation decreases so slowly. And Ursula's group has looked at this as well. Tom Reichert has a new paper, and they've plotted the difference in the angular rotation speed between the particles and the gas in their vicinity. And they find that during the plunge-in, there are large differences, but just after the plunge-in, during this slow spiral-in, those differences are much, much smaller. And so there is a certain amount of co-rotation. It could also be the density. So people have talked about the possibility that the density is much lower. It's actually, a lot of the material has moved out to larger radii. And so that could be another reason why the drag force might be smaller. So this needs more work. But the suggestion here is that the jury is still out on whether it's really we need more physics in the simulations, or whether we just need it's a numerical issue. So, what am I doing for time?
8 minutes left, sorry.
So I just want to mention, without getting into too many details, that many explorations with parameter space have been carried out. So I just tried to list them here. And one that hasn't really been looked at, I guess, and that was mentioned briefly as something that could be done yesterday, is to look at the evolutionary stage of the primary and when it actually enters the common envelope. So for a given mass of the primary, a given 0-age main sequence mass, looking at different evolutionary stages with everything else in the simulation the same, and I mean the initial separation maybe not, but all the other parameters, and exploring the dependence. Sure. Something that could be done. Initial eccentricity is something that's only been done in one paper as far as I can see. Code comparisons, we've talked a lot about that. There has been some amount of that done in the literature. So like Ursula mentioned, she's compared the two codes that they use, the SPH and AMR codes, in this study in particular. And then we also tried to reproduce some results from Sebastian's paper. The initial conditions are a bit different. We don't have initial rotation of the envelope, and they do. But qualitatively pretty similar. And then interestingly, I thought it was nice that Phil looked at two cases with rotation, with initial rotation and without initial rotation. So basically looking at initial conditions more similar to Sebastian's and more similar to ours. And some of the features that are different between ours and Sebastian's, like this initial periastron where the separation is lower than the following periastron, are actually reproduced here. But other things are not reproduced, like we have a smaller period, and Phil finds that the non-rotation case has a larger period, I think. So, but I mean, at least it's there has been some stuff done with very similar initial conditions and comparisons between results. We should do more of it. And I should also say that another priority is to compare the results of 3D global simulations with 3D local wind tunnel simulations. So the talk by Rosa yesterday, but I mean, this can help us to understand the limitations of both kinds of approach. So I think we want to go in steps, from 3D global, 3D local, 1D, and then the population census steps. So ideally, we'd compare adjacent rungs of the ladder. So how best to set up the problem? There's basically three issues in my mind: the initial conditions, the resolution, and gravitational softening, and including extra physics, which is a big topic, but I have only one slide because we discussed it a lot yesterday. Initial conditions, okay, so I think this method, or slight variations thereof, has been adopted by most of the groups now, and it seems to me to be the best thing we have going. We sort of guarantee a hydrostatic equilibrium in the core by solving this modified lane ambient equation. What is the best way to cope with the ambient medium? So there were questions at the beginning of my talk, and do we want to model an AGB wind, for example? Or do we we want to take an analytic model. We want to just put an exponential envelope. Then we could, so we actually tried that, but in the corners of the box, we have problems because of the high gradients. But we could, smooth that into a uniform ambient medium that's a larger radius, and then that could lower the mass of the ambient medium and pressure. So there are possibilities, and we need to think more, I think. We can discuss it, how to deal with that. Is the relaxation run a good idea? Is it necessary? For us, we find that we do get our stability of our core, the core profile is a bit better when we do a relaxation run, but at the same time, the actual density of the core gets reduced during the relaxation run. And also, we find some grid effects when we do the relaxation run and just leave it in one place on the grid, whereas if it's moving around, it's more stable because the errors seem to add, they don't add, they're more random, so they don't just add up. And so how much of a difference would it make to initialize the primary in the presence of the secondary? So that's something that Sebastian looked at in his thesis, but no one's actually, to my knowledge, actually tried this. Possibly Ursula's group has tried, but it's something that is just proved. So we initialize it in isolation, but actually it should really feel the potential of the secondary as well. We really should be studying and presenting stability in our simulations, in our papers, I believe, especially at the core and at the surface, where the scale heights are the small. And then the Roche-Lebeau phase, how important is that? These are sort of questions to discuss. And then the initial rotation to use, that one I can try to answer using some of Morgan's results, recent results, where he finds that starting from the Roche-Lobe separation, Roche-limit separation, and moving in, so here it's at co-rotation, the envelope is at co-rotation with the orbit, but then moving in, the angular velocity of the, mean angular velocity of the envelope actually remains fairly constant until 1 is where the surface of the primary is. And so if you just calculate what the separation would be, you assume co-rotation there, and then whatever your initial separation is, you can compute what the rotation should be. And for our model, for example, it's about 30% of the co-rotation. We use 0, other people use 100. So the answer is probably somewhere in between, but that's a good way to estimate it. And so all the codes have to consider what lowest base resolution to use, highest resolution, gravitational softening or smoothing lengths, how these quantities vary in space or between the particles, and how these quantities vary in time. That's basically what we need to figure out, and how do these things affect all the various quantities we're trying to measure. And then finally, the extra physics. So there's convection. Convection could be important because of diffusive mixing, as well as transporting energy. It doesn't just transport energy out, but it spreads energy in all directions. We don't know what effect that will have on the unbinding, but it's probably important. So that also would affect things like alpha. The radiative transfer and cooling, for modeling transients, this is crucial, as was discussed, the high mass regime, and again, the efficiency, like in Jason's talk. Recombination, a lot of talk about that. There's still a question of viability in some people's minds, and then how to implement it. Accretion and jets, there are a lot of questions here, a lot of issues. We're just beginning to explore this, as are other groups. Will the companion mass decrease substantially? Will it aid in the unbinding of the envelope? Will it affect the shaping of the envelope and the planetary nebulae? Will it help to explain the high momentum outflow seen in planetary nebulae that can't be explained very easily? Again, for transients, people are interested in jets. Accretion onto the primary core, so that's not only onto the companion, but onto the primary core after tidal shredding of the companion. This won't help to explain the small observed separations, because you're taking the energy not from the orbital energy, but from the potential energy of the accretion energy onto the secondary, or onto the primary, but it could help to explain the unbinding. Dust, magnetic fields, how important are they really? Is this a priority for our simulations? It's not an energy source. You can convert kinetic energy to magnetic energy via a dynamo, but you're not going to get more energy out. And then nuclear energy, timescales are long enough. This could also be important. So I guess I could leave this up here and we could have the discussion. Thank you.
So one question about the drag, and maybe Rosa, yesterday I was really jet lagged, so I didn't catch on some of the things you said, but I think, you know, your striker formalism, which we look at, which is giving you the drag strength, mostly dependent on density contrast and velocity contrast, also has an one little parameter to do with the max speed. Now, I look at what the max speeds are inside the simulations, and they vary quite a bit. For instance, if you use very low mass companions, your initial max speeds are highish, like 2 or 3, high for me, and then they go subsonic afterwards. If you have more massive companions, they tend to be around the sonic point or subsonic. But sometimes there is a transition between sonic and subsonic, and the striker formalism would imply that there is quite a change in the gravidrag. Yeah. Now, what is interesting is I've tried to plot these 3 parameters of the gravidrag strength to see what is causing the sudden halt in spiral. It's not a halt, but it's this change in regime, right? And the density and the velocity contrast, usually you can see some simulations there's more one and some simulations more the other. But have you noticed anything to do with a change in gravidrag to do with a change in max speed of the simulation, of the companion?
The relative.
Yeah, so this is the max speed of the companion relative to the medium that it's in.
Medium.
Yeah.
We haven't actually computed that yet. I saw that in your paper they do compute that, and I had the graph there, but I had to take it out because too many slides. But yeah, so we compare it to the Bondi-Hoyle-Littleton so far. You've compared it to what you actually measure, and then you put that into the Bondi-Hoyle-Littleton in terms of the relative velocity. You actually measure it first from the simulation using spheres, right, around the particle, up to different radii and so on. So yeah, that's important too. So that's why we couldn't compare our results with yours because we haven't. But we should do both.
Because that pertains to the question: is the gravidrag represented in the code right? Do you have a comment?
Yeah. So I think there's a couple important things here. One is that if for whatever reason the relative motion between the object and the surrounding gas becomes subsonic, then at least in the context of a uniform medium, traveling in a straight line, there's in theory an opportunity for pressure to readjust the surrounding structure, and your essentially your drag, your dynamical friction disappears.
Yeah.
And
there's no clump behind.
So this is a big deal. Whether the degree to which that exactly plays out in our circular orbits is somewhat less certain, I would say. So,
so even the theory may not be applicable potentially.
I think that's potentially true. And
that's actually what we argued in the 2008.
Exactly. So I think that as a second thing, that as one of those terms in that equation is a Coulomb logarithm, and that says what's your maximum length scale compared to your minimum length scale, at which you're forming some wake. And the maximum length scale is kind of the coherence length of the problem. It's like the separation of the binary. But the minimum length must be, if you just have a softened particle, that's your softening radius. And so I think that's why in this phase where your softened particle is like moving relative to gas, there's softening radius dependence. Whereas like before they come together, when they're separated, we actually don't see softening radius dependence. And I think that's because gas is like flowing into these like sort of rotating structures around the point mass rather than like trying to traverse directly through it.
I think there's something else too, and that is that the initial plunge corresponds to a large tidal distortion of the envelope. And that I think is making the gravitational drag not strictly local. And but there's this transition to a regime where it does become local, and you can express it in terms of a dynamical friction like
exactly. So putting that in the language that we talk about in terms of these density gradients, I think what we see is that near the very edge of the star, you're in the like, say you're just outside the star, you would say my local density is 0, I feel no drag force, but you know that there's a star next to you, and so that's like a really extreme density gradient. Your drag is coming from the material just inside you. And so I think the regime in terms of the plot that we were just looking at, that comparison, where we expect there to be some useful comparison, is before they start to stabilize. And I think your plot makes the really nice point that by everything to the right of 10, the envelope, such as it was, has been totally like messed up. You know what I mean? And lifted up, and so the density compared to the original density is completely different. And I think this nicely shows that once you reach that regime of starting to stabilize, part of the reason is because the density structure is completely different.
It should be noted the Ostraker calculation is a perturbative calculation.
Yes. Yeah.
So it's linear perturbation.
Yeah. Yeah. Exactly.
Maybe over here was, I think, second.
You
want to go first?
Okay, so I have a question, not necessarily to you, but just to IMR people. So one of the things which freaks me out with IMR codes is this hot stuff. Now, I usually thought that it's much smaller. I think from Ursula papers.
Our density is 10 to the 4th lower.
Yeah, so
Yes.
I mean, I thought your stuff overall on the box is much smaller than these two solar masses. And I just wonder, and I understand that you decided to choose so in order to bring down the temperature of the surrounding media. But I'm just curious if anyone have done a comparison, well, a study trying to understand the effect of this hot fluff on the outcome, such that you change the temperature and the density and see what will the result is, or at least like putting some energy inside and see how much energy is needed to remove all that stuff outside of the box and evaluate the effect. I mean, energy plus the gravity which you have. So I'm just curious because everybody has with hot fluff, but I do not understand what the result of this hot
A
fluff.
very, very helpful referee, I'm sure is in this room, made us do that in the Giacconi 18 paper, and we did. So we have a low density, but obviously the temperature's through the roof, and I understand the desire of wanting to lower that. So that's our setup, and we found that for the boxes we used in AMR, in the grid calculations, the work needed to move or displace that fluff is negligible. But if you go to bigger boxes, so we made the box bigger, same simulation, then it starts to have an impact. And it's all tabulated in the Giacconi 18 paper.
I think a useful like order of magnitude metric is you can ask if you have some ejecta that you care about. Say I care about the outer 10 to the minus 3 solar masses.
Right.
You can ask, have I swept up 10 to the minus 3 solar masses of background? And if you have, you've completely changed that outermost distribution of mass.
Yeah, we think it's affecting the stuff that's moving out supersonically, and that stuff will slow down as it interacts with the ambient. And we've estimated all the energy terms, all the work terms that it will do on the ambient, and it's consistent with what we're seeing. But we don't think it affects what's happening at the center with the oil.
Yeah, I agree with that. I mean, we tried to make it so that the fluff mass in the box is maybe 1% of the total. And just live with the temperature that we have to have for that.
Yeah, okay. So I'm going to make a comment, and the comment's going to come after I ask all the simulators in the room a question. Here's a question, all right? I think I know what the answer is. So the question is that how do you treat the secondary? Okay, so I believe you guys treat it as collisionless particle. I treat mine as a collisionless particle, a dark matter. How do you treat it, Paul?
Used to treat it as a cloud of particles like the core, but now just as a single particle.
So it's a collisionless particle, right?
Always collisionless,
Yeah. How do you treat it?
Same.
Same. How do you treat
We
it?
often have a main sequence formed by SPH particles, so it's just a bunch of particles.
Bunch of particles.
Yeah, I mean,
Right.
they interact not on the gravity.
Okay, yeah. So one thing that might be the frontier, all right, is actually how do you treat the secondary?
Sure.
Okay, because the thing is that like we've been treating it as a dark matter particle, or most people have been treating it as a collision particle, but the fact of the matter is that like it's a dense star, and you actually calculate what the bonding radius would be when it enters the envelope. It's about a third of the radius of the star, right? It's a sizable fraction of it, okay? And so basically,
That
it
can't be right.
may not be correct to treat it as a collision particle. It may actually be better to treat it as a hard sphere going through the star.
I think where you're saying
Probably
it's a
bound-
third of the radius of the star.
The main
If
star.
the mass
Right.
ratio is
Right.
1 to 3, it's a third of the radius
Yeah.
of the giant star.
Oh, okay, yeah, sure.
It's a sizable fraction.
Otherwise, the secondary wouldn't be bound.
You have to
Right.
get down to like a planetary mass before the geometric cross-section becomes really important.
Yeah.
That trade-off is like brown dwarfs, I
Yeah.
think,
Yeah,
for
right.
typical parameters.
So, I mean, like, and that could be the difference basically between the fact that you are able to like eject a huge fraction of the envelope.
No, I mean, so
Because
for
that-
most of the common envelope simulation, it wasn't the point particle, but for mergers, we use both, and in fact, it was.
Oh, I see, you use a point particle,
Point part-
collisionless,
Oh, it's.
or SH particle?
It's a it's not normal speed particle. It's
Not-
just
what's that?
gravitational.
It's just, purely gravity, no pressure terms.
Yeah.
Oh, when you say point particle, I mean, we always have a size to the companion, even though it's collisionless. In fact, we
Right,
treat it the same
that's
way
right,
as
that's right,
as a core.
but the question is that, does it interact hydrodynamic
Yeah.
of the rest of the
So
gas?
there is no hydro terms.
No,
for
no,
the
we don't-
most of the
we don't do that.
solutions.
So,
Yeah, I think that's
it may not be correct to treat that as a collision particle.
So we
That's
cal-
not correct.
Well, we calculated that if you have a planetary mass companion,
Yep,
then the not the gravel drag, but the hydro drag matters,
Right.
particularly in the latent spiral.
yep.
But if you have anything more massive than that, like from 0.1, 0.15 above, then it doesn't matter, it's really low.
So why do you say that? I don't quite understand, because like,
Really
doing
small?
it, if it's a hard sphere.
Compared to the-
Yeah, but you can calculate the
Stuff can come in,
hydrodynamic drag.
And then stuff will bounce off the surface.
Yeah.
So it acts like a boundary, so that will act as a hydro drag.
But it's much lower than the gravitational drag if the mass is high enough.
Okay.
Just a point about that, which is also the idea of the subgrid models, right? I mean, so, we did with the first paper, those two, with a subgrid model for accretion and not a subgrid model for accretion. Because really, if you don't have a model for subgrid accretion, what happens? Your material just, on the secondary, just, comes in towards the secondary and builds this sort of quasi-static atmosphere. And that has pressure in it. So, one of the reasons why now we're going back, we're trying to develop more intelligent subgrid models for this problem is most subgrid models have been built for star formation, where you pretty much have stuff, Bondi flow just screaming inward supersonically, and that's not what's happening here. So, what we found is when we put in the subgrid model, we may have been reducing too much pressure. We were sort of, the Krumholtz subgrid model sucks pressure out in a way that may not be physical. But if you don't have a subgrid model, now you've got this big fluffy ball of gas that wants to accrete, but can't accrete. So I think there's a big issue sort of
Krumholtz,
that
of
needs to
course,
be
is
resolved.
designed in an environment where you have radiative losses. You have radiative losses, like an optically thin environment,
Yeah.
right, the star-forming region, whereas, that model has a way of radiatively losing that
Right.
extra pressure. Here,
Right.
you don't.
You
So,
don't.
unless you have neutrinos, as we've talked about. Yeah. You were.
So I have a sort of a naive question. So if I understand correctly, the hot fluff, you care about it only when it's static, right? If you somehow have an outflow, you don't need the hot fluff.
Once it blows away, yeah.
What?
Once it blows away, sure.
Right. So only when it's static, you need the hot fluff to maintain static. Can you just say that the fluff is really dilute and cold, but just whenever you have an interface between some fluff, which is easy to identify, and something that is static by some criteria, saying that its difference in the primitive variables compared to its initial primitive is something, then okay, make this fluff, when you just solve the Riemann problem, say, actually, you know what, put here something that's slightly more dense and hot, but only if the cell hasn't got any dynamics, which you can quantify by different primitives or something.
Well,
Change it.
I think some kind of an Eulerian scheme that was fluff aware, or that vacuum aware, let's say.
Fluff aware.
Vacuum aware, would be kind of an interesting advance, and I think it would help for a lot of things.
I've done something like that before, and it worked pretty well. I think, and then I decided that I cared a lot about that outermost skin that was actually doing the interaction, and that's the only place where you introduce any problems, is right at the juncture.
Right.
So I went in the
Terrible.
direction of making a very, very low mass background instead, but I think in practice that worked well, and you just don't make your time step respect those outer zones, essentially, and you make sure you're not doing it, you just reinforce them every step.
Yeah.
that work particularly fine if you don't care about the outer stuff, essentially.
So an early version of the repo also supported true vacuum.
Yeah.
So like they would just like solve if one of the side would vacuum, it would just solve the true Riemann problem for vacuum concept, right?
Yeah.
But in the end, we just completely remove this because you're always running into strange edge cases. with this state.
Yeah.
And so while it sounds philosophical, or it sounds interesting conceptually, I think it's very hard to get really run stably in actual simulations. We just completely gave up.
That's probably especially true if you're doing a Cartesian mesh on that.
I was going to thought I'd make a couple points that, along the sort of the drag raised an interesting point that you had asked, Brian had asked about, physics that you can extract as a piece of the problem, and the drag is a good example. You do the Windtunnel simulation, which is not the complete environment, but you can do it at higher fidelity, for example. Get some principles, see how that applies or does not apply in the context of the actual simulation. Other things are the same way. Accretion, you have accretion simulations, which you can learn about. Then you have to take a kind of subgrid model that's based on higher fidelity, put it into the system. So that kind of approach in other subfields as well. So we have the kitchen sink simulations, but those are not the, you have to use pieces and then put them in the kitchen sink.
Yeah.
So you can't get everything from a kitchen sink simulation at the end of the day. The other thing I was going to say is just the standard, one wants to risk, Kepler versus Newton. I keep thinking that way. So, in the MRI subset, so the accretion disk simulation field, there's many simulations over decades, but it's not fed back into an improvement of, say, the Shakura-Sunayev basic model. So as an end-term product of all this, it'd be nice to gain principles that can feed back into a kind of either the alpha formalism for those customers, but one risks, if there's not a standardization and a standardization of the set of problems studied, kind of this kind of fragmentation, and we just have Kepler's, not the general. That's
Yeah.